2.6, we're going to be talking about rational functions. A rational, remember, is a fraction. So we're going to be talking about a fraction of a function in the numerator and a function in the denominator. The most common basic one is 1 over x. They have a t-table of what happens if you had 1 over x. And what we have here are some what we are going to call boundaries, because we're going to get to how is the graph bounded, where does it begin, where does it end, how does it approach asymptotes, and go from there. So what you see here in this t-table, it says as my y values, because remember that's what f of x means, as my y values get closer and closer to negative infinity. That means it's going to keep getting out here, negative, 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 negative. So as the y's approach negative infinity, the x's approach the 0. And then as the y's approach positive infinity, it's going to approach 0 as well. So these points up here are just the points that the t-table had. So if I was graphing these, I would connect my dots. And we would call the line x equals 0. So x equals 0 is the vertical line here. Sorry. And we would call that the vertical asymptote. And hopefully we remember from previous year that an asymptote is, in case we don't, an asymptote is a line the graph approaches but never touches. Okay, so here, as the y's approach 0, we get this line, because that's y is 0. We get the horizontal asymptote. So these asymptotes are the boundaries of this polynomial. As the y's, and I'm going to come back up here, as the y's approach negative infinity, so here's my y values, as they approach negative infinity, as I get closer and closer down here with y's, my graph gets closer and closer and closer to x0. We don't need to worry about that negative, positive stuff. As my y's get closer and closer and closer and closer to positive infinity, notice my graph is approaching 0 as well. So that gives us our asymptotes. So on page 2, we have the definition of a vertical and horizontal asymptote. As our y's approach infinity, x approaches a number. And if we have a horizontal asymptote, as our y's approach a number, the x approaches infinity or possibly negative infinity. Make sure you check out page 190. When we are looking at the asymptotes of a rational function, we're going to have some guidelines to help us find those asymptotes. The graph of a function has a vertical asymptote at the 0, which means x-intercept, of the d of x. Now notice d of x is the denominator. So if we set the denominator equal to 0, that means we're finding our vertical asymptote. The graph can have horizontal asymptotes, and it's determined by comparing the degrees of the numerator and the denominator. So here's that comparison. If the numerator exponent, or degree, because they mean the same thing, is less than the exponent of the denominator, y equals 0, which is the horizontal x-axis, is the horizontal asymptote. If the degrees are the same, then we say the line has a horizontal asymptote at the fraction of whatever the leading coefficient of the numerator is over the leading coefficient of the denominator. And if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. So this is how we're going to find vertical and horizontal asymptotes. It's going to be based on, vertical asymptote is based on what the denominator, where is it 0, and the horizontal asymptote is based on the degree of the comparison of the numerator and the denominator. So on page 3, we're going to compare the degree of the numerator and the denominator in here. So here, the degree is 1 in the numerator and 2 in the denominator. So we would say the numerator is less than the denominator, and according to what we just said, if the numerator is less than the denominator, then the horizontal asymptote is actually the x-axis, because x to the first is less than x squared, so the horizontal asymptote is y is 0. Okay, now when I look at here I have 2x squared is equal to 3x squared, because they're the same degree, they're the same exponent. Therefore, the horizontal asymptote is the leading coefficient. 2, leading coefficient, 3. So it's at y equals 2/3. Horizontal asymptotes are always going to be y equals, because that's what it means to be a horizontal line. Here the degree is 3x cubed, and it's going to be greater than the 3x squared. So if it is 3 is greater than 2, we say there is no horizontal asymptote. However, it will have a slant asymptote, but we're going to worry about that in another section. So right now we're really only focusing on, is it a vertical asymptote and horizontal asymptotes, and actually we're also going to be finding zeros, and from zeros we can also find domain and range. But for right now, when it comes to asymptotes, the only thing we're looking for is vertical and horizontal. On page 4, we're going to be able to find the domain of our picture, vertical asymptote, horizontal asymptote. So here, we're also going to throw in a little bit more information, because in your homework tonight, you are going to be asked to not only find the vertical asymptote and the horizontal asymptote and the domain, but you're also going to be asked to find x-intercepts as well as the y-intercept. So let's start with, we're going to leave the domain, and we're going to look at that in a minute or two here. And we're going to start with the vertical asymptote, part B. The vertical asymptote is determined by the denominator equal to 0. So when I solve, and this is our vertical asymptote, and VA, you're going to see me abbreviate all the time vertical asymptote for that. So I get -5. X squared is +5/4. When I square root, I get 2 answers. The square root of 5 and then the square root of 4 is 2. These are going to have approximations. Punch them in a calculator. You're going to get plus and minus 1.12. Alright, so part C, our horizontal asymptote, and again, abbreviation, horizontal asymptote, is based on the degree of the polynomials. So I have 3x squared is equal to negative 4x squared, highest degree, highest degree. Therefore, the vertical asymptote, which is always a y equals, is the leading coefficient of the numerator over the denominator, so negative 3/4. All right, now I'm going to come back over here to part A where we have the domain. The domain comes from the vertical asymptotes, because our graphs are pretty much always going to be everything except whatever asymptote, whatever point on the x-axis it's going to approach but never touch. So I would say it's everything except the plus minus root 5/2. You will be asked to make some sketches, and you can do that fairly quickly with your calculator. So y equals, the numerator, you're going to want to put it in parentheses, 3x squared plus 7x plus 2, divided by the denominator. Again, put it in parentheses because otherwise it will be read incorrectly by order of operations. And we see a quick picture. Now, when you see these lines drawn straight up and down on your calculator, that's just your calculator, depending on which model you have. If you have 83, 84, newer, whatever, you may not even see those lines. Those are the asymptotes. They're actually drawing in the asymptotes. When we draw our asymptotes, and here's our xy axis, when we draw our asymptotes at 1 and a little bit more, we use dashed lines. So there's the positive 1.12 and the negative 1.12, and then our horizontal asymptote is at negative 3/4. Okay, so we now know our boundaries. We do need to find our x-intercepts, y-intercepts. We can kind of see what they are from here. You could blow this up, but in order to find the x-intercepts, we set the numerator equal to 0. So in this case, and solve. 3x squared plus 7x plus 2 is 0. So we're going to factor this. 3x, x, 2, 1. So we're going to get an x-intercept at negative 1/3 and at negative 2. So negative 1/3, about there. Negative 2 for there. One thing that we do need to clarify is between two, in this case, vertical asymptotes, this horizontal really doesn't exist, the horizontal. So the horizontal is actually extended from the verticals, and there isn't a horizontal inside of the between the two. So when I look at my picture or I pick some points, we also we're going to see that it's always going to approach our asymptotes. This point can only approach in one way. If I look at my picture, notice this one has a down one. So that's the only way it's going to approach. So we have an x-intercept. We know it's not going to cross the x-intercept here. We know it's not going to cross the y-intercept here because it's approaching an asymptote. We got the x-intercept. It's approaching. It's going to keep approaching this asymptote. It's not going to touch the y, but we do need to know where is it going to touch my y-axis. And the way we find a y-intercept is by just making all of our x's 0. So to find a y-intercept, make x 0. So if I come up here, 0, 0, 0, we find the y-intercept is 2/5. So we'll say it's about right there. Alright, so we're going to be approaching our asymptote to the right and approaching our asymptote to the left. This is pretty standard of all the information you're going to need to be able to find. So let's start with domain. The domain is the how far left and right our picture goes. It goes from negative infinity to 5/2, negative 5, root 5 over 2, but doesn't touch. It goes from negative root 5 over 2 to positive root 5 over 2 and doesn't touch. And then it goes from positive root 5 over 2 to infinity. So if we use our interval notation, we would get negative infinity to root 5 over 2 without touching. Then we would go negative root 5 over 2 to positive root 5 over 2 without touching. And then root 5 over 2 to infinity without touching. So that's our interval notation. This is just our real, old school kind of notation. Both answers would be acceptable. And here we have a graph using all of our x-intercepts, y-intercepts, and our new two concepts of vertical asymptote and horizontal asymptote. All right, when we come down here, this is not a rational. Or it is rational because it is a fraction. But what happens is that it doesn't work because we have an absolute value. An absolute value is going to give us a whole bunch of different rules. If we put it into our calculator, numerator x plus 10 divided by the denominator absolute value of x plus 2. When we look at this, we actually end up having two different asymptotes. If you look at the sketch here, we're going to get an asymptote at -1 and at +1. The positive one is up there, and then the -1, so that it comes down there. And you can kind of see that in there. Because what happens here is that the degrees are the same. So the leading coefficient is -1 for everything less than 0. Here's 0. Here's my less than, so there's my negative. 1 over 1, so leading coefficient is just 1 for all of my x values greater than. So that's where that comes from. It's more of just a visual look at how once we start throwing in absolute values and square roots, we're going to have different types of asymptotes. All right. You're going to definitely see this type of problem again, where you're going to be given an equation and you're going to be given a restriction from 0 to 100, where P represents some kind of percent of a smokestack. And what you're going to be asked to do is find some information about it. So it says the current law requires utilities to remove 85%. The legislator wants to increase that to 90. So how much additional costs would this be? So what we have to do is we have to substitute in the 90 and subtract what it currently is at 85. Do some calculator work, and you can come up with how much more additional is it to go from 85 to 90, and you get the cost of about $266,666.67. Because it's money, we do need to round appropriately. But you do see this type of a problem again, where they're going to give you the formula, they're going to give you the information, and all you have to do is plug it in. We don't use decimals because it told us our P is between 0 and 100, not 0 and 1. So we just use the 85 and the 90, not the decimal. Alright, so here's another one of those same type of questions for you. They're going to give you the equation, and then they're going to ask you some, find the different pieces of information. So in each of one of these options, we're going to plug in the 1,000. Then we're going to do it again for the 5,000. You're going to do it again for the 10,000. And you're going to do it again for the 100,000. Alright, and you're going to come up with these solutions. I think this was 550, 150, 55 cents. And you're just finding this pattern of how, as the number increases, the cost decreases, because that's what all this C, average cost, all of that is talking about. So in order, what is the horizontal asymptote? Well, we did this because it said find the average cost. So that's kind of part A. Part B, what is the horizontal asymptote? Well, that's based on the degree of the function, and then they are equal. So 0.5 over x is 0.5 over 1, which is y is 0.5. And again, asymptotes are lines, so they always need to be in line format. Don't just say the horizontal asymptote is 0.5. The horizontal asymptote is y equals 0.5. Alright, so what that means in words, what does this represent? You need to know the wording of a real life situation. You can't just go, oh, the asymptote is this. You have to know what it means. It means my graph is going to continuously approach and get closer and closer and closer and closer and closer and closer and closer to 0.5, or the cost approaches 50 cents, or the average cost, because that's what we're finding. The average cost approaches 50 cents per unit. So make sure you can give a word explanation for the word problem. And that's going to be 2.6.